Today, we have a weird problem, and I don't really know what to call it, but it was sent to me by someone in the Discord chat. Be sure to check that out. I'm going to show you how to solve this problem, which is a pretty complicated Lagrangian mechanics problem in Python. Specifically, it'll be nice because we'll solve it using no paper. And believe me, a problem like this by hand takes quite a while. Once we obtain Lagrange's equations symbolically in Python, we'll then convert them into numerical Python functions, which we'll use to get the actual coordinates as a function of time. With these coordinates, we can then animate the system and see what's going on with the kinetics of the system as well. If you enjoy this content, as always, please be sure to like and subscribe. I have lots of Lagrangian mechanics tutorials on this channel, from simple things like the double pendulum, all the way up to simulating a three-dimensional spinning top, which is probably the most complicated thing I have on this channel. Anyways, this is a good one, so I hope you enjoy. So there's nothing too fancy for the packages today. It's pretty standard for Lagrangian mechanics problems like we've done in the past on this channel. We got NumPy as always, matplotlib. We'll make a little bit of animation at the end. And this is good in a way almost to check that our problem actually does what we think it should do physically. We have SciPy for numerically solving the differential equations that we'll get. And we'll get those differential equations symbolically using SymPy. And that's sort of the best part about doing this on a computer, is that no pencil or paper is needed to go through taking derivatives of functions over and over and over again. So our problem looks like this, and it doesn't really have a name. You could call it whatever you want. You could name it after me. And it was sent by a user on Discord, actually, and I thought it was interesting, so I'd make a video on it. And so there's a wall here, and there's a spring. This is our coordinate system, x and y. So this is positive x, positive y, negative y. And we have a spring here, spring constant k, and a natural length L0, meaning you compress it, it pushes out, you stretch it, it'll pull back in. So these are the parameters of the spring. It's connected to a mass m2. It's connected on wheels to this surface up here, so it can sort of roll back and forth. There's a pendulum attached to this mass, and then underneath the spring you also have another mass sort of hanging below. So the thing will kind of go back and forth, and the pendulum will swing to the side, and you know, a bunch of other stuff as well. And so the interesting thing to note is that the entire system, the state of the system, depends only on two angles, theta 1 and theta 2. So if I tell you what theta 1 and theta 2 are, I can construct any configuration I want out of this system. So obviously those will be the free variables we use when solving this problem, because they're the easiest. So theta 1, of course, is this angle here. And as the sort of spring contracts, theta 1 will get bigger. And as this thing sort of swings to the side, theta 2 will change. So we'll define all the symbols that we need in this problem in SymPy. So the first two obviously are t and time, g for gravity. We have L1 and L2 representing the lengths here, and then this length here. M1, M2, and M3 for the mass of all three masses. K for the spring constant, and then L0 for the natural length of the spring. And that's just using this simple code here. And I have, as always, I can look at these symbols. These are SymPy symbols. I can perform operations on them. I can square them. I can take the sign of them. So these are just symbols that I can do symbolic manipulation with, essentially. And then theta 1 and theta 2, these are a little bit different than just constant symbols. These are functions of time. And so the way I define them is I go sim.symbols, the same way as here, only I specify them as a function. So they haven't been defined yet, so if I look at them, they're sort of in an indeterminate state. Like SymPy knows that they're functions, but it doesn't know what they're functions of yet. And when we solve the system, of course, they're going to be functions of time. And so that's what I do here. I say theta 1 and theta 2, which I've defined above. These are functions of time in the end. So you give me a time, and theta 1 and theta 2 will change. That's the physics of the problem. I also define the derivatives, right? Because if I have theta 1, so I'll run this cell. If I have a symbol theta 1, and this is a function that depends explicitly on time, I can take the derivative of this as simp.diff as follows. And it'll sort of save it like this. And then I define my derivatives, right? And I also define my second derivatives. And you might wonder, why am I defining the derivatives and second derivatives? Well, the whole Lagrangian system, the equations of motion, depend on the first derivatives and the second derivatives of theta. So it's good to have them defined so I can reference them once I go through this derivation. So these are all defined here once I run this cell, as long as I go like this. And so now that we have theta 1 and theta 2, when we describe the kinetic and the potential energy of this system, it's a little bit complicated to write in terms of theta 1 and theta 2. It's easier to write in terms of the x and y coordinates of these masses, right? And so that'll be easy to write the kinetic energy once we have that, and the potential energy as well. So first we're going to take theta 1 and theta 2, and we're going to use it to find the x and y coordinates of all three masses here. So x1 is really simple. It's L1 cos theta 1. You can see from this diagram here, L1 cos theta 1. This gives you the x position of mass 1. Similarly, minus L1 sine theta 1 gets you the y position. So that's what I have here. So the x position of mass 2, this is 2 times L1 times cos theta 1. That's this distance here, and I multiply it by 2. There's a symmetry in this triangle, and that gives me the x position of this mass. Now, the y position is just equal to 0 because it's stuck here. If I look at my coordinate system here, it's just constant. It's stuck to the rollers, and it will roll back and forth. For mass 3, so that's what I have here. I have x2 is 2 times x1. That's like symmetry from this triangle, and y2 is equal to 0. For x3, well, that's just equal to x2, the position of this mass here, that's x2, plus L2 sine theta 2 for the x position, if I look at this triangle, and L2 cos theta 2 minus L2 cos theta 2 for the y position of this mass. That's exactly what I have here. So I'm just sort of starting at this position here and slowly building my way up with triangles to get the x and y position of all three masses. Now, if I look at the x and y position, if I look at these values, explicitly, everything is written in terms of L1 and the symbols and theta 1 of t, right? Because eventually these are all going to be functions of t. Probably the longest one is x3. So everything is written sort of in terms of L1, theta 1 of t. These are all the parameters I need. And now I can take the derivative of these with respect to time to compute the velocities, which is needed for the kinetic energy. And that's what I do below. So I define both kinetic and potential energy. So the kinetic energy T of this system, let's look at this system. Well, the kinetic energy just comes from the motion of all three masses. Nothing else has mass. So that's just 1/2 mv squared for all three of these masses. But the potential energy, there's a few things. There's the potential energy stored in the spring, and there's the gravitational potential energy of M1 and M3. So we have to define those carefully. And so to get T here, I just take sim dot rational 1. So this is 1/2 times M1 times V squared. So I take dx dt squared plus dy dt squared. Pretty simple. Just using the same terminology, right? If I have x1, I can also take the derivative of x1 with respect to time, and it will return something like this. And it will save this whole thing like this. So I just add all three of these together for x1, x2, and x3. Now the potential energy, well, there's just this mgh for all three masses, which I have here, plus the potential energy in the spring. You have to be careful with this one, right? So I have 1/2 kx squared, right? That's the potential energy of the spring. But x is equal to x2 minus L naught. And why is that the case, right? If I look at this diagram here, well, x2 is the position of mass 2, and L naught is the natural length of this spring here. So if I stretch it out, there's potential energy stored in the spring. So the difference between where this is located versus L naught is the potential energy. If x2 is equal to L naught, well, then the spring is just, in its standard position, and there's no potential energy in the spring in that case. So that's how you think about x is the difference between the natural length of the spring versus where sort of x2 is located. That's the potential energy stored. It's either squished or it's pulled from that position. So x is equal to x2 minus L naught. And so what I can do is I define potential energy like this, and I have 1/2 k times x squared, the sort of stretched, the difference in the spring. And L is just t minus v. This is classical Lagrangian mechanics. And so I can define these and actually look at the Lagrangian. And it's pretty long. It's not an easy Lagrangian. And to do this by hand would certainly be time consuming. So here's my Lagrangian. And now that we have the Lagrangian, we simply compute Lagrange's equations for each free variable. And that's what I do here. So I have dl d theta 1 minus ddt of dl d theta 1 dot is equal to 0. That's the first Lagrangian equation. Same thing for theta 2. So two free variables, two Lagrange's equations. And that's really simple to do. So if I have L here, as I do, If I want to compute the derivative of L with respect to anything in here, I just take simp.diff. I could even compute the derivative of L with respect to gravity. Not that I would want to do that, but I could do that. But here I want to take the derivative of it with respect to theta 1. And I get something that looks like this. And because I defined theta 1 dot above here, I can also take the derivative of it with respect to theta 1 dot, or the derivative of theta, which is what I need here. And so I can take the derivative with respect to anything, like I do. And so here's the derivative of L with respect to theta dot here. And then outside of that, there's also a derivative with respect to time. And I simplify these two equations. So I get LE1 and LE2. It takes a couple seconds to run. These are my two Lagrangian equations. And they're pretty long. And they're complicated. And you think, well, how the heck am I going to solve these? These are complicated equations. Well, what's interesting to note about Lagrangian mechanics and obtaining Lagrange's equations is these are obviously highly unlinear with respect to theta 1 and theta 2, etc. But if you look at the second derivatives, whenever the second derivatives appear, it's linear. It's like ax plus by plus cz, that linear equation. Well, I have two variables here, theta 1 and theta 2. The second derivatives, theta 1 dot dot and theta 2 dot dot, show up as linear factors only in these equations. So I have two linear factors, theta 1 dot dot and theta 2 dot dot. I have two equations. That's a system of linear equations in the second derivative. Now I'll repeat that. It's a system of linear equations, in two second derivatives. So I can solve those systems of linear equations in the second derivatives really easily. You can solve a system of linear equations very easily. And that's what I do here. So I have my two equations, LE1 and LE2. By the way, they're expressed like this. They're not equal to something, but in SymPy, it assumes that this is all equal to 0. So when I plug this into my solver, it says, okay, I'm assuming this whole expression is equal to 0. So I solve this equals 0 and this equals 0. And I want to solve for the second derivatives, which I defined before. And so I get the solutions, and they're returned in a sort of dictionary-like format. And if I want to access a particular one, I just need to go theta 1 dot dot. And that will return for me, this is what theta 1 dot dot is equal to. So this is what the second derivative of theta 1 is equal to. And I have something that looks like this. This is just a differential equation. It's a second order differential equation. Theta 1 dot dot equals this. Same thing with theta 2. What does theta 2 dot dot equal to? Well, I solved Lagrange's equations for the second derivative. Now I have a second order ODE. Theta 2 dot dot equals all this. Pretty long expression and probably not the kind of thing you want to solve by hand. But thankfully, we have numerical packages for this. So to summarize, we have the second derivatives of both theta 1 and theta 2, and they're both equal to long expressions. We obtain these by Lagrange's equations and solving for the second derivatives, since they were a system of linear equations. So now we have them explicitly in terms of the second derivatives. So in Python, we can solve systems of second order ODEs, right? And so I went through this in my pendulum video in a lot of depth, where I solved the double pendulum in Python. And I talked about how ODEs in Python, you have to split them up into systems of first order ODEs. So if this is your introduction to all this, I suggest watching that double pendulum video. Anyways, we define Z1 as d theta 1 dt and Z2 as d theta 2 dt. That gives us two more variables. And now we've turned a system of two second order ODEs into a system of four first order ODEs using this trick above. And I suggest to pause the video, think closely about this, and also check out my double pendulum video where I explain it in quite a bit more depth as well. So we have four first order ODEs. The dot dot dot, of course, is the long expression that I showed above. And we need to convert these symbolic expressions into numerical Python functions. Then we can integrate them to actually get the solution. So to do that, I go dz d1 dt underscore f means it's a Python function. It means it takes in a bunch of numbers and it returns a number, like a typical computing function. And so it takes in all these variables here. These are all the arguments to the function. Of course, it depends on t, g, k, l0, m1, m2, m3, all these parameters here. And what I'm looking for is theta 1 dot dot. This is theta 1 dot dot depends on all of these. And it returns, this simp.lambdafy returns a numpy or a typical Python function that takes in numbers, returns numbers. So here I have these z1 dt underscore f. These are functions. And then the same thing for d theta 1 dt, which of course is just equal to z1 in this system of equations here. So very simple. And to sort of express what I mean by that, if I go z1 dt underscore f, I can feed it in a bunch of numbers. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I can feed it in 5, 6, 7, 8, 9, 10, 11, 12, 13. And it will return a number. So I've given it all these numbers here, and it returns a number. So this can be used in a numerical integration library. So we have systems of first order ODEs in Python, and I always solve them in the same way. There are 4 things I want to solve for: theta 1, z1, theta 2, and z2. So I define my vector s. S is everything that I want. If we're going to use an ODE solver in Python, what we do is we take in a function that takes in s as an argument. It also takes in time if our system explicitly depends on time. In our case, there is no dependence on time on any of the things in the system, right? It's not like the spring constant changes with time or anything. It's constant throughout the problem. But if it were dependent on time, then it's important that it also takes in time. But we write a function that takes in s and time, and it returns ds dt. This is a differential equation. It's like saying ds dt depends on s and t. This is a vectorized form of saying like dy dx depends on x and y, right? That's a differential equation. So it's like the vector form of a differential equation, and it can be sort of expressed like this: a function called ds dt that takes in s and t and it returns ds dt. So our system of ODEs can be fully specified using ds dt. If you tell me what ds dt is as a function of s and t, that is the differential equations that describe our system. So here I define ds dt. It takes in s and t, like I said. So s is a vector that contains theta 1, z1, theta 2, and z2. It takes in the time t, and all these additional parameters that sort of depend on the system as well. And it just returns ds dt. So this is the first component of ds dt, d theta 1 dt, dz1 dt, d theta 2 dt, and dz2 dt. So this is our function. Then we can use this function in a numerical Python solver that is used to solve differential equations, and this will get us our solution. And so now that our function is all properly formatted, we'll solve the system of differential equations using the ODE int method of SciPy. And so here I define some times I want to solve over, 0 to 40 seconds. I define g, k, all the masses. I'm going to change this to 2 kilograms, or 1 kilogram, so they're all sort of slightly different. The 2 lengths, they're going to be the same for now, and L naught is equal to 1.5 times L1. So that sort of gives some parameters. By the way, setting L naught equal to this value means that this spring is stretched when it's equal to about 1.5 L1. If it was 2 times L1, it would have to be, these would be pulled apart. Theta 1 would be equal to 0, and that's when the spring would be relaxed. So it's relaxed when it's 1.5 times L1. So it sort of looks like this geometrical shape. So these are numerical parameters, and I just use ODE int. It takes in the function we derived above. These are some initial conditions of theta 1 dot, theta 2, and theta 2 dot. Are the times we want to solve for, and all these additional arguments that we need to pass to this function as well. So we can solve it. We can obtain theta 1 and theta 2 if we look at our answer like this. So we can look at our answer. It returns an array like this. So this is theta 1 dot, theta 2 dot, and then at the next time, and then at the next time. And so it returns like 4 different parameters per time. If I only want like the first column, I can transpose it using .t. And I just take the first thing, and that gives me the first thing that I want, which is theta 1. And I can do that for both theta 1 and theta 2 like this. And I can plot them as a function of time. And you get something that looks like this. And now these plots are interesting, but you can't really see what's going on with the system. And so for that, we'll use matplotlib's animation library. So in order to animate, what I really want is a function that takes in theta 1 and theta 2 and gets all the different x coordinates of the system. So I wrote this function, get x1, y1, x2, y2, x3, y3. It takes in theta 1, theta 2, and it will give us all these 3 coordinates, which I can then draw using an animation. So it's the same as above that I already went through at the beginning of the video, only now I'm using numpy.cos instead of simpy.cos. and I just get all the x coordinates and y coordinates that depend on theta 1 and theta 2. Then I use this function to actually get these arrays. It'll return these arrays, and I give it my solution of theta 1 and theta 2. It's able to get all the x and y coordinates as arrays like this. So finally, here's the code to animate. First, you need a function called animate. This is typical when you do animations in Matplotlib. It takes in the frame number of the animation I, so the ith frame, and I'm setting some data of the lines here. So first, I'm drawing a line that goes from 0 to x1, y1, and then to x2, y2, and then to x3, y3. So it's sort of connecting those dots. And so if I trace this out in the picture above, it goes 0, here, here, here. So it's just doing something that looks like this. But I also want a line that draws a line here as well that sort of represents the spring, because that's also sort of important in the problem, is connecting this line here. So for that, I just need to go from 0, 0 to x2, y2. And that's what this second line does here. It goes from 0, 0 to x2, y2 for the ith frame. Then I set up a figure as I would normally in Matplotlib. I set the background to K, so black. I turn off the X and Y ticks. I start the lines with 0 data points. Remember, there's 2 lines, this one and this one. So they're empty right now, and they're connected in a certain fashion, the line width and marker size. I set my X limit and Y limit. Then I use the animation library function to create an animation. So it takes in the figure that I defined above. It takes in my animate function as well. I'm going to animate for 1,000 frames. And this parameter isn't super important, but I set it equal to 50. And then I save my animation. So I'm saving it at 25 frames per second. And there's a reason why I do that. If I look at my times here, right? And I see how many times there are t where t is less than 1. So these are all the times from 0 to 1 second. And I look at the length of this. There are 25 times per second, discrete. So if I save my animation at 25 frames per second, since there's 25 times per second, it's in real time. Now, if there were twice as many times in 1 second, and I were to save it at 25 frames per second, then it would be going in half speed, because it would only go from 0 to 0.5 seconds per 25 frames. So I specifically do this so that it plays it in real time. So you have to synchronize this FPS argument in animate with the density of times when you actually solve your differential equation. And you can relate the two, and sometimes maybe you want to slow it down, and then you can compute the factor, like how many times slower is it than real time, for example. If you're dealing with things on a nanosecond scale, then you'll definitely want to slow them down. And you could say, well, this is 10,000 times slower than real time, or whatever you need. So anyways, I save the animation as a pendulum. It takes a couple seconds to run, and then eventually we get the animation as well. So here we have the animation of our system. So this line here represents the spring. We have the mass hanging underneath, and then we have the pendulum here. And you can sort of see how energy is transferred between kinetic and potential energy in the system. This certainly isn't a beautiful animation, but it does the job in showing what do the kinetics of this system look like. Anyways, if you enjoyed this video, please be sure to like and subscribe, join the Discord server, and check out all my other Lagrangian mechanics videos as well. If you like this video, I think you'll really enjoy the simulation of a spinning top video. That was super fun to make, pretty difficult, but probably the most complex thing that I currently have on my channel. Anyways, have a good week, and I'll see you next time.